Very good morning and welcome to the lecture series session on EC402 Nanoelectronics. My dear students, the last class we have discussed about the scanning electron microscope and its working and the applications of scanning electron microscope. Today we are going to discuss about another type of electron microscope named transmission electron microscopy. And what is the basic difference between the operation of these SEM and TEM, transmission electron microscopy. That also we will discuss today. Okay. So transmission electron microscopy is a microscopy technique in which a beam of electron is transmitted through a specimen to form an image. Actually, the electron beam is passed through the film that or the image or the material or specimen whose image is to be enlarged and to be viewed, isn't it? The specimen is most often an ultra-thin section less than 100 nanometers thick. An image is formed from the interaction of the electrons with the sample as the beam is transmitted through the specimen. So we have the arrangements to transmit the electron beam through the specimen, and there will be different lenses provided, and of course the construction details, all those things we will discuss one by one. Okay. The image is then magnified and focused onto an imaging device such as fluorescent scan. Usually this imaging is done on a fluorescent scan through which we can see the specimen in an enlarged view of the specimen in a light that is photoluminescence effect is there for the fluorescent scan, so you can see the image in the form of light. Okay. The transmission electron microscopes are capable of imaging at a significantly higher resolution than light microscopes. That also we know. That is why we go for electron microscope, because it can enlarge the specimen about 300,000 times. Okay, such a very large magnification with greater resolution is possible with transmission electron microscope, and even almost all the electron microscopes. So its working is different from one type of electron microscope to the other. Okay. The transmission electron microscopy can provide microstructural crystal structure as well as microchemical information with high spatial resolution from each of the microscopic phases individually. That is the main advantage of using TEM. What is that? It can be used for knowing the or for providing the microstructural that construction. That is, microstructural means the lattice formation of the material through which that particular specimen has been evolved or the specimen has been produced. So that information can be available with this by using transmission electron microscopy. Then what are the other one? Crystal structure of materials. Of course, crystal structure of thin films materials or the surface materials, like that. Okay. And also there will be microchemical information. That is the combination of that lattice. That is the combination of the material through which that particular material has been evolved. That what is the chemical composition, and that information also we can get with a very high resolution, and that is with a very high spatial resolution in all the 3 dimensions. Actually, that is the main important thing. Here we will be getting almost that 3-dimensional specimen information into at least 2-dimensional with all the information possible. Okay. And TEM is therefore a very powerful tool for material characterization. That is the main reason why TEM is used for characterizing nanostructures or nanomaterials. Okay. TEM not only helps to know the nanomaterial structure, property, correlations, but also in the development of alloy or improved performance. Actually, TEM helps to know the structure, that is crystal structure, that is microcrystal structure, and property correlations. What are all the constituent parts in that particular crystal structure, and what are all the alloy? If it is an alloy or a compound, then what are all the alloys which actually constitute that particular material? All such information is possible to get from TEM microscopy. Okay, spectroscopy we say. In inelastic and elastic scattering are 2 ways in which electrons interact with material. That we know already. In SEM we have seen so many kinds of specimen interactions, out of which In TEM, we are very much interested about inelastic and elastic scattering. Of course, inelastic is not very much interested because inelastic will not give out the information with regard to the material. But elastic scattering is very important. That we will see one by one. In inelastic scattering, leading eventually to absorption. Why inelastic scattering is not because it eventually absorbed by that specimen, that actually by the specimen and system itself, and that must be minimized to obtain good image contrast. That is the main reason, because inelastic scattering must be minimized to a great extent in order to get the image contrast in a good manner, since it contains no local information. With regard to the specimen, no local information. What are the local information? Means information which is readily available with regard to that particular material, because inelastic scattering, which will be directly passing to the particular material directly, it will not be having any scattering or any kind of refraction possible. Okay, but what about elastically scattered beam? Elastically scattered, that is always subjected to diffraction. That is very important. Okay, why elastically scattered beam is very much important here in TEM? Because elastically scattered beam is always undergo diffraction, which provides information about the sample. Okay, the lattice defects modulate the amplitude and phase of the incident and diffracted beam. That is the main important thing. The lattice defects, if there is a lattice defect in the crystal structure, of course, that will be modulated, and the amplitude and phase of that incident beam, diffracted and incident beam, will give the information with regard to that lattice defects. Okay. In TEM, an electron beam with energy of 100 kilo electron volt or more, and even it may up to 3 mega electron volts. Of course, such a large voltage will be developed, and that is the electron beam energy that is allowed to go through the thin specimen, which is mostly less than 200 nanometer. Usually, the material which are under the nanometer range will be usually examined with the help of electron microscope. So in such cases, actually, we make use of the energy produced by the electron beam. That may be in this case, the TEM case, that is transmission electron microscope, it will be of the order of 100 kilo electron volt or more than that. Sometimes it may be up to 3 mega electron volt. Such a large voltage is developed in the electron beam for electron beam transmissions through the specimen. Okay. TEM offers special resolution down to an angstrom, high magnification up to 10 raised to 6, and it can work as a microscope and a diffractometer. That is another important thing with regard to this TEM. TEM can be used as a microscope, that is electron microscope, for analyzing the material and materials or material surfaces, its composition, microcrystal structure, and all those things. And also it can be used as a diffractometer. That's also very important. You know what is a diffractometer, because you might have learned it in the physics class. Okay. Keeping inelastic scattering of the electron small has a supremacy. This demands specimen thickness between 10 nanometer and 1 micrometer. Actually, in nanometric range, all these informations are required to be done for materials which is in the nanometric range, that is 10 nanometer to up to 1 micrometer. Actually, it is not 1 micrometer, it is about 100 or 200 nanometer, maximum up to 1000 nanometers. That is 1 micrometer. Okay, that is that range only. It has been given that particular range. Okay, the resolution depends on the thickness. High resolution TEM demands specimen thickness in nanometric range. Of course, for high resolution, in order to have a high resolution in the readings taken in the measurement of that material or the characterization of the material, of course, the material thickness must be, or the specimen thickness must be in the nanometric range. Okay. Now, what are all the important basic systems which actually constitute the TEM that we have to know now? It has three essential systems. What are those essential systems? Yes, first we know the electron gun, that we will see its pictorial view, and that particular schematic diagram also it has been given, and I will just show you what are all the important things and explain how it works. Okay, electron gun. What is the function of electron gun? As usual, it produces electron beam of very high intensity energy. Okay, high energy electron beam. Okay. The image producing system, that is the second one. So what is the image producing system? Which consists of objective lens, that you have to understand, which consists of objective lens, movable specimen stage, that is There is a specimen holder which can be moved with reference to that particular beam directions and all those, so that an operator can move it in order to facilitate to the correct position of the specimen. Okay, and intermediate and projector lenses. Of course, these are all the imaging system. Image producing system consists of objective lens, movable specimen stage, and intermediate and projector lenses. And of course, there will be an aperture that will be the primary and secondary aperture is also there, that I will just explain to you in detail. Okay. Then a image recording system. What is the recording system here? Here the recording system is the fluorescent screen. Okay, that is the CRT screen. It is a very similar to your computer screen because it's a computer screen only, really speaking. Okay. In TEM, electron beams can be focused using the magnetic fields and can hence be used for imaging. So one thing you have to understand here, this is not an optical instrument, which is an electron beam instrument. So here the enlargement of the object or image are done with the help of electromagnetic lenses. Okay, you have to know this one. There is no that glass lenses here. There is no optical lenses as such here. Here it is the electromagnetic or electrostatic lenses. Here in TEM we have electromagnetic. HCM also the same thing. We have the diffraction coil and all those things, and there will be that electromagnetic lenses which can enlarge the specimen. Okay, which can enlarge the specimen image, not specimen image. Okay. Okay, now the magnetic field can be used as a convex lenses for electron waves. As with conventional optical lenses, the lens aberrations are difficult to correct even in magnetic lens. Even if the magnetic lens are used, of course, if there is an aberration, what is the aberrations? If there is any corrections to be made, then that corrections to be made, just like in what we feel in optical lenses, the same thing we have to do in the case of magnetic lens also. So that is not very simple. Okay, that is why the aberrations are difficult to correct even in magnetic lenses. But generally, there are ways and means to do this one. How the aberrations can be, the optical aberrations through when the beam passes through the lens can be done. That are all possible. Okay. However, the intensity distribution of the electron waves leaving the specimen can be magnified by an electron optical system and the resolutions of less than 0.0 nanometer are possible. See that resolution, even if we are having this kind of arrangements and all those things, this intensity distribution of electron waves leaving the specimen, that is our interest is to know the image quality, image lattice and all those things. So whatever is the beam which is passing through the image has to be magnified. That magnification is of very much importance in the case of electron microscopes. So here such a magnification is done by electromagnetic lenses, and the electron optical system can have a resolution not less than 0.1 nanometer. That is possible with this kind of system. See the uniqueness of this kind of machines, the versatility of this kind of instruments to know the very minute, very nanometric range materials and structures which can be analyzed. See, we are actually very much blessed with such kind of instruments. That's why we can analyze bacteria, viruses, and even our coronaviruses too. We can observe with this one and getting the structure of it. Okay. Now, so this is the actual TEM schematic diagram. This is the schematic diagram in which that particular beam direction, that is path of beam from electron gun downwards to up to the fluorescent screen has been shown here. Okay, so its line diagram is shown here. So first we have the electron gun here. So this is here we have to mark electron gun. I didn't mark here as electron gun. If there is an electron gun just like this one, an electron gun you can show. Then that electron gun will be producing its electron beam that is scattering here and there, of course. And first condenser lens will be making its collimated actually, which will be making a passage by making it focusing, and that focusing is done very clearly with the help of second condenser lens. So this is the second condenser lens. So from this second condenser lens, all the the beam which are actually out of that out of the range, which are all that are all that is nullified. Okay, and only those beams which are to be directed to the sample has to be focused like this from the second condenser beam, and that will be passed on to a condenser aperture, a small aperture here, and that can be adjusted. That is what I have told you earlier. This condenser aperture can be adjusted, so that is coming here, and then the sample is placed between the objective lens and the aperture. Okay, this is the sample which has to be examined for analyzation and for knowing the characterization. And then the beam passes through the sample, which penetrates through the sample into scattered inelastic and elastic scattered electrons, and that will be actually passing through this sample where we have to know the characterization of the material, and that is then passed through objective lens. And from this onwards, actually, we have the magnification of the image which is obtained here in the form of electron beam, and that beam is then passed through the objective aperture, that is the aperture which is made available here after this objective lens, and then the aperture can be that select area of the aperture. We can just adjust, I told you already, we can adjust the aperture area so that the specimen, the actual specimen area which has to be analyzed can be adjusted and made available, and that can be enlarged with the help of first intermediate lens. That is, this is the first intermediate lens through which this beam is passed through, and then it is then focused again and given to the second intermediate lens. So it is then passes through the second intermediate lens, and where this is further focused exactly what the area of the material has to be analyzed. That is further focused, and that is given passing through the projector lens. So that projector lens is the one which actually magnifies all this projected image that is onto the screen, that is the fluorescent screen placed here. That may be a computer screen, a CRT screen. Okay, so that we will be getting the enlarged version of the image which is observed here. So that is the basic working of this one. That working I will just read it once I have just explained to you now how the beam is collimated here, and that is passing through the sample, and then it is passing through the objective and selective aperture areas, and then going to first intermediate lens and second intermediate lens, where again it is that particular lens is actually focusing, and that is enlarging and focusing the beam to a projector lens where it is magnified. This image is magnified to several times, so that that magnified image will be made available over on the fluorescent screen. Okay, that is shown here. Though it is symbolically shown, this is actually a pictorial view of this one. Gun is here. This anode that actually we're passing through this one. So here, this is the condenser lens, the first, second condenser lens here in this part. Then the specimen is here, sample specimen. Then actually this is the objective lens. We have this one objective lens here. Then again it is focused and given to the intermediate. Of course, selective aperture area and objective aperture area are there, but it's not shown here anyway. But it is there. Okay, in order to direct this beam exactly over the that particular area of the fluorescent screen, so that that particular area of the image area of the sample that is directed through this aperture and then projector lens. Then it is coming to the projector lens. Intermediate lens is here. This is the first intermediate lens that will be enlarged to a certain extent. Of course, that beam is now collimated, and that is actually given to this particular area. Then second lens is first and second intermediate lens will be available here, and then it is passed on to the projector lens where it is magnified further, and that magnified view of the image of this sample through which this beam has been come will be now made available on the fluorescent. Okay, so this is the basic working of the TEM. Now we will see. So what are all the important interactions taking place? So just like a specimen interaction we have seen in the case of SEM, here we are having different kinds of course, unscattered electron will be there, inelastic electron will be there, elastically scattered electron will be there, and there will be some characteristic X-rays depending upon the energy of the incident ray. Of course, there will be cathode luminescence. So many kinds of such interactions will be taking place in the case of TEM also. But our interest is to know the elastically and inelastically scattered, because unscattered electron we should not know it, because it will be directly passing through this one. So that will not give much information with regard to the specimen. And we will be concerning the elastically scattered and inelastically scattered. The elastically scattered will be giving you the diffraction, and that diffraction information will be giving you the correct details about the specimen. Okay. Now, the electron gun fires the beam of electrons. The gun accelerates the electrons to extremely high speed using the electromagnetic pulse and voltages of up to several million volts. I told you it may be nearly about 3 million volts in order to have such a very high speed electron emission to take place. That is necessary. That high voltage is necessary. That is what the electron beam is, electron gun is doing. Okay, the electron beam is focused into a thin small beam by a condenser lens. I told you already, which has a high aperture that eliminates high angle electrons. I told you the extra electrons, the emissions or electron beam emissions, that is what we call the high angle electrons, that will be eliminated. And only the collimated beam of electrons that will be passing through. The electron will zoom through the ultra thin specimen, and that will be passing through the specimen, and parts of the beam are transmitted depending on how transparent the sample is to electrons. Actually, the penetration of the electron through the sample and reaching to the other side of the sample depends upon the thickness of the electron. Okay, that depends upon the thickness of the electron and how transparent the sample is to electrons. That is very important, because transparent here means it is not transparent as we see in the case of optical sense. It is actually the transparent with regard to the penetration of electron beam. Okay, that how transparent the sample is to electrons. The objective lens focuses the portion of the beam, that is image. Objective lens focuses what? Objective lens actually focuses the image beam of the electron beam. Actually, it is an electron beam, image beam, that is emitted from the sample. That is actually emitted from the sample because it is passing through the sample with interactions. Of course, this electron beams are actually emitted through the sample. The image beam is passed through the intermediate and projector lenses. It is sufficiently enlarged and strikes the screen. Okay, that I have already discussed here. When the beam strikes the phosphor image screen, light is generated, which causes the image to be visible to the operator. So the operator can view the visible that on the screen. The image view can be very clearly seen in the on the image screen, that is the phosphor image screen. Okay, that is the fluorescent screen actually. The image produced by the TEM is called micrograph. Usually the image produced by TEM, that is transmission electron microscope, is called micrograph, and that is seen through the fluorescent screen. Okay. Now I told you already the basic difference between STM and TEM. Here in STM, what we are doing, we are actually focusing the scanning beam of electrons over the surface of the material, isn't it? This is the specimen. So here it is a biological sample. Over the sample material, over the sample, it is directed and it is hit over the surface. So that so many interactions take place. And such secondary electron interactions, actually such specimen interactions are actually secondary electron interactions that are actually directed to sensors or detectors. So that sensors or detectors actually gives the information with regard to the sample. Okay, so that is actually happening in the case of SCM, that we have already seen. But in the case of TEM, what is happening? TEM, this electron beams are directly passing through the biological sample. Okay? We have taken a biological sample, of course not other material, a biological sample. So what happens? It penetrates through the sample depending upon the thickness of the sample. So it penetrates through it so that it actually creates the image of the sample like this. Okay, so some of the electrons after interaction, it will be passing through this one as inelastic electrons, like that, so that it will be passing. So that's why here so many electrons are actually hitting over the sample surface, but it is some of that inelastic and elastic electrons which are all actually passing through this one that creates the image here. And over the image viewing screen, that is fluorescent screen, we get the exact image magnified with the help of the projector lens, isn't it? Okay, that is the basic. So here actually the transmission of the image from the sample to this fluorescent screen, we can see it in the, on the fluorescent is actually direct from the material surface to the fluorescent screen. Here, but it is actually through the secondary electrons, which is actually detected by a detector, and that detector information is given through the computer screen or that fluorescent screen, where we can see the image of the sample. Okay, that difference is here. That you have to understand what is the basic difference between these two. Okay, now we will see the area through which the very few electrons are transmitted look darker. The area through which very few electrons are transmitted means that area is somewhat thicker, that is the darker, and that areas are actually usually denser areas or thicker areas. That is why electrons cannot penetrate to it completely. Okay, the lighter areas of the image represent those areas of the sample through which more electrons were transmitted. Actually, in lighter areas or thinner areas, more electrons can be transmitted, so that they are looked to be a lighter areas, which are actually looked to be lighter areas. Lighter areas means actually more that it will not be giving any dark areas or dark spots. Okay, dark areas. Okay, or that is usually considered to be less dense areas of inner areas. The electrons that pass through the sample is classified as, so that are what are all the different kinds of interactions takes place that we have seen in that diagram, schematic diagram. And the most important are unscattered electrons. The unscattered electrons pass right through the sample after inciding. Inciding means incident, and that is inciding, that is incoming rays, that is the inciding with the sample, that is the beam which hits on the sample surface, inciding with the sample without interaction with the sample atom, that is the unscattered electrons. Okay, the transmission of these electrons is inversely proportional to the thickness of the sample. So the how many number of electron rays or beams which are passing through that particular sample depends upon the thickness of the sample as far as the unscattered electrons are concerned. What about the scattered electrons? The scattered electrons are collected by magnetic lenses and it forms a pattern of diffraction spots. So actually scattered electrons give us the actual pattern of the image or pattern of the material sample in the form of image or diffraction spots. Okay, this diffraction pattern gives information about the orientation and atomic arrangements in the area probed. So we have probed an area in the specimen. So on the specimen we have probed some area where we have to analyze and we have to find out the alloy or whatever is the that atomic structure or whatever characterization we want to know. This diffraction pattern gives the idea with regard to that particular sample. Okay. Now, the information that can be investigated using TEM. So, what are all the information we can get from the TEM method? The TEM method can be used for knowing the morphology. The morphology means the size, shape, and arrangement of particles which make up the specimen as well as the relationship to each other. So, the size, shape, and arrangement of the particles, that is lattice structure only, which makes up the specimen as well as the relationship to each other. Then crystallographic information. See, morphology can be understood. Crystallographic information could be understood. What is meant by crystallographic information? The arrangement of atoms in the specimen and the degree of order. So, what is the degree of order in which the atoms have been placed or which has been actually made? Okay. The compositional information, the elements and compounds the sample is composed of. So then I told you already for alloy material there will be different compounds through which only that particular material has been evolved. So such compositions could be understood. So these three informations could be very clearly understood with the help of transmission electron microscope. Okay, then what are all the applications of TEM? The applications, of course, we can find out these features with regard to the sample, and the main applications are actually to know all these informations where we have to go or what we want to do. TEM can be used in various industries from medical research. See, the medical research, it is very widely used where it is employed to investigate viruses and bacteria. So I told you already the coronaviruses and the other kinds of bacteria, different kinds of bacteria, that are all concerned with the biological samples that could be identified, that could be studied, that could be analyzed with the help of TEM, that is transmission electron microscope. Okay, TEM has also been used to determine the melting points of nanocrystals. So TEM can be used to determine the melting points of nanocrystals. So for knowing the melting point of nanocrystals, TEM can be used. How it is used? Heating of nanocrystals by the electron beam can cause melting, which can be identified by the disappearance of the crystalline diffraction. See, the beam that is a very high energy beam that will be heating upon the surface of the sample may cause to make the nanocrystal that is actually that order in which it has been arranged will be disrupted, isn't it? So that order will be disrupted, so that the diffraction will be disappeared. So that kind of things, so such kind of effect can be identified by the disappearance of the crystalline diffraction. So that also will be giving you the operator an idea of the kind of that is what is the melting point of the nanocrystals with which that particular material has been involved. Okay. Now, what are all the challenges? Challenges means what are all the difficulties faced by TEM? That is the challenges. The difficulties, main challenges or difficulties in TEM investigation is the specimen preparation. I told you here the specimen has to be prepared. That is a very thin film, thin structure of the order of some 10 nanometers to some less than 100 nanometers. Such a thin film has to be prepared. So that is the specimen. So the specimen preparation is it's a challenge. It's a difficult thing. Obtaining specimen thin enough is a big task. The electron scattering information in a TEM image originates from a three-dimensional sample. Actually, the electron scattering information in the TEM image actually originates from a three-dimensional structure, isn't it? It's actually a sample is actually a three-dimensional structure, sample. But it is projected onto a two-dimensional detector. Actually, the information which is given from the three-dimensional sample is converted into a two-dimensional information through the two-dimensional detector. Okay, that is the challenges which we usually met in doing analysis with TEM. But even if such challenges are there, still we can have the information done by making the specimen that because of technological advancement is such that. So still this TEM is a very good tool for characterization of nanomaterials, nanostructures, nanosystems, nanofilms and all. Okay. So I think with this we conclude this TEM here. I hope you have understood the working and the main important parts of TEM very clearly. So thank you very much for patiently hearing my lecture session. Thank you.